324. 324.
I'm gonna screen black.
Hang on. I gotta switch a setting so that you guys can see them. Thanks, Lil. All right, guys, we're on page 324 in our science book today. And yesterday, we had the world's greatest discussion on the carbon cycle. Any other day would have probably been pretty boring. You breathe out carbon, plants breathe in the carbon, carbon goes in the ground. I thought we had a really great conversation about it yesterday. I was pretty excited about all the connections you guys made to decomposition, space. Yeah, you guys did a fantastic job with the discussion yesterday. I was really proud of you guys. Today we're going to continue talking about a part of the biosphere kind of after it's the biosphere, okay? So we've got fossils. Lily's like, what? The biosphere after it's the biosphere?
That don't make sense.
That don't make sense. Okay, so we got fossils, okay? I said 324, but actually I lied. I mean page 326. So we're not doing that activity right now. We're going to go to page 326. You should see a tiger on the bottom of the page, okay? All right, so, sorry, we just got back from recess. They were a little wild. Bless you. Okay, so I'm going to start reading. When some ancient organisms died, their remains were covered with soil, sand, or some other sediment, okay? Over many centuries, these sediments hardened over and around the organism's remains. So we kind of talked about this yesterday. When an animal dies, some of it gets kind of picked on and eaten by scavenger animals in the woods or the desert or wherever it is, right? But then there's some bones and some other pieces that are kind of left that nobody eats or messes with. And they take way longer to decompose, the bones do, than the meat, right, and the skin, that part of and the organs, okay? Most of the skin and the organs will get eaten by other creatures out there, or it'll decompose. But the bones don't really decompose. So we kind of talked about yesterday how that some of the stuff decomposes and gets eaten by the fungus and turned back into dirt. But it takes a super long time, if ever, for the bones of a living animal or human to turn into dirt. So what it's saying here is those bones are laying there and those remains, and over many centuries, which a century is 100 years, so it's saying over many hundreds of years, the ground kind of just grows over and around it, and different layers of dirt and rock form over these bones. Yes, Jason?
Isn't there meat inside of the bone?
There's marrow inside of the bone. It is a softer tissue, but when a body dies, though, that marrow hardens. It's kind of spongy. It's like a soft spongy material. The outside of your bone is very brittle and hard. The inside of your bone is called marrow, and it's a spongier texture. But when you die, that hardens too, and so the bone is hard all the way through. Okay. I don't know about how it works.
Hollow?
It's not hollow.
Yeah, it is, but it has marrow in it. It's the marrow dog.
It has marrow in it. Okay. All right. Fossils are the remains or traces of ancient organisms preserved in soil or rock. Write that one down. Keep track of that. Tomorrow, we're going to have a worksheet that kind of goes over everything that we've talked about this week. The carbon cycle, fossils, and then this stuff from the other day, symbiosis, the mutualism, commensalism, parasitism, okay? So tomorrow, it's not a quiz, but we will have a worksheet that kind of brings it all back together tomorrow. But for today, we're going to write down fossils, which are the remains or traces of ancient organisms preserved in soil or rock.
So fossils.
Okay. All right. Almost all fossils are found in sedimentary rock. We will learn more about the types of rock when we get to geosphere, but there are different kinds of rocks. That's all you need to know for now, okay? Scientists can use fossils to learn more about ancient environments. Scientists know that modern animals that live in a warm climate have certain characteristics. What could scientists conclude if they examined fossils from Antarctica and saw that these fossils have characteristics of warm climate animals? So what they're saying is, right now, if I were to analyze,
The saber-toothed tigers.
well, no, I wouldn't analyze a saber-toothed tiger because it's not alive right now. I take an animal that I know is alive right now and that does well in this kind of climate. Name something. I don't know. A fox? Fox?
A monkey.
Fox or a monkey, and you look at the kind of bone structure it has, and you compare it to the bones of a fox or a monkey from Antarctica, and it's the same, but long, long ago. That tells scientists that Antarctica maybe wasn't always as cold.
Maybe it was once on the equator.
Maybe it was once on the equator, or that land, because Sean says, well, remember the land all shifted around back in the day. True fact. Okay, so maybe the area that's now Antarctica down in the south, very cold, used to be up higher where it was a warmer climate, and those kinds of animals could do well. Possibly, yeah. Pangea, you are right. When it was all one big landmass, it was called Pangea. Nailed it.
Who said that?
Cain.
How does he know that? Because he's smart cookie.
Because he's Cain. I don't know any other reason other than because he's Cain.
Circle K.
All right, Circle K. Okay, so like I said, scientists conclude that Antarctica must have been much warmer back then, okay? Sometimes different characteristics are shown by comparison of the bones in modern animals to fossilized bones. In the 1880s, the fossilized bones of an organism named Smilodon were discovered. Smilodon is a type of large cat popularly known as the saber-toothed cat because of its large fangs. The fossilized fangs are larger than the fangs of modern lions and tigers. Scientists generally agree that the Smilodon used its fangs for hunting. However, they're not sure whether it used its fangs to grab the prey or to bite the prey, like to eat it. Right? Like, well, not like a vampire to suck its blood, but just like it could grab it and like drag it where it wanted it, or it would like chomp down on it. That's what they're trying to say. They're not sure which one. But so they can compare. We have tigers and lions now. Tigers are getting to be, they're endangered, but we still have tigers, and we can look at what their fangs and their teeth look like now. And yes, their teeth are large,
But they're not sticking out of their mouth.
but they're not like huge, like almost like, they look like, they almost remind me like elephant tusks. They're so big, or like rhinoceros, like, because they're so big. If you look at that picture down on the bottom, you see on the left on that picture what the actual fossils look like. On this side, those are actual saber-toothed fossils that they found. And in this picture to the side of it, do we have actual pictures of saber-toothed tigers? No, because there were no cameras back then or modern people. So we don't have actual pictures, but based on what those fossils look like, they know that it probably looked similar to this when it had its skin and fur and everything, okay? So scientists are pretty smart and they can figure that kind of stuff out.
Lily one day will be able to do that.
One day Lily can do that for us. Maggie.
So when they found those fossils, could they like, if there was still like maybe like, oh no, never mind.
What?
I already answered my question.
All right, Maggie answered her own question somehow. Okay. So how do these bones become fossils though? Why don't they eventually break down like all of the other parts?
Because of the type of rock it's in.
Because of what?
The type of rock it's in.
The type of rock that it's in?
But some stuff.
Okay, how did it get, how did that type of rock get around?
Because of the time that it was like that.
Okay, Zeke says it was just that time era that it went down into the ground. Okay. Lily, what do you think?
Because it's harder than muscle and skin, so
Okay.
it can't like decomposed?
Lily says it's just harder than muscle and skin, so it's not going to break down like that. Fiona?
Because it's kind of like a rock. They're hard and they don't really decompose what you do because they're not like meat or skin, or they're more like flexible or something or movable. So the bone is basically kind of like a rock, and rocks don't decompose.
Right. Fiona's comparing it to a rock. Like the bones are hard like the outer surface of a rock. The rocks don't break down. They just crush, right? And that would be similar to what would happen to a bone, right? It doesn't disintegrate or melt or turn into a liquid or a goo or dirt. It would just crush into like little bone dust, okay?
Okay, so I think I remember this. I learned about it somewhere on a TV show or something. But so like the fossils, once they die, the bones are on top of the surface, and as like more stuff decomposes like and stuff, and it changes, the bones like sink down into the bottom, and then it like turns into hills, and then it takes millions, like a long time.
It does take a long time.
And then they turn into bones, and then once they get well, they don't turn into bones, but they turn into hills, like the material they're on after it changes and evolves, and then it goes and then it settles up in the rock, and that's why you find like printings of bones in rock or like creatures. Like,
Okay. So let's read. Figure this. All right, Shawnee Poo, what you got?
Okay, so last year we used to when I was playing a little alchemy, like it said when you combine sand and like mud and made a rock, so maybe it like kept on piling up around it.
Okay, so he said different combinations of different types of sand and mud and rock form together, and in different temperatures and circumstances, they form a certain type of rock. So let's read. You're not far off, okay? All right. Fossil fuels at the top of the next page. Like the plants of today, plants that lived millions of years ago used the energy and sunlight to make food. They stored the sun's energy as sugars, and the plants eventually died. Layers of sediment, which is dirt, built up on top of the dead plants. Okay? Over millions of years, like Zeke said, pressure from the weight of the layers of sediment pressed the dead plants together and formed something called peat. P-E-A-T. Not to be confused with the name peat. This isn't a person. It is a type of ground, okay? As the peat hardened, it turned into a sedimentary rock called bituminous coal. All right, got it. It's a soft coal, okay? As it was buried even deeper, the coal changed into a metamorphic rock called anthracite or hard coal. So the deeper it's getting, it's going from a soft coal, and as it gets pushed down deeper, it gets into a different kind of rock, and it is called, what did I just say? Anthracite, and then it's a harder coal. The deeper it goes, the harder it gets, okay? Bituminous coal and anthracite are types of fossil fuels. What is a fossil fuel? Okay, a fossil fuel is a material that formed from the decay of ancient organisms and is used today as a source of energy. Is that a word we need to write down? Yes. Fossil fuel is a material that formed from the decay of ancient organisms and is used today as a source of energy.
Fossil fuel.
Fossil fuel.
Okay.
Material that formed, it's on page 327. You can copy it down. Fossil fuels highlighted in yellow is standing out in the middle of the page, and then all the words after it. Material that formed from the decay of ancient organisms and is used today as a source of energy. Okay. All right. If you look over on the picture on the right-hand side, on the left side pictures, in the top left, you see the little pink box that says coal. And the top picture says dead organisms in a swamp form peat. And you see that kind of darker soil in the picture. That's the dead organisms that were on the beach, and they turn into this peat. Okay. And then the peat gets covered with layers of sediment. So in this case, it looks like they're on a beach. I'm guessing it's kind of like sand. As the ocean tides come in and out, it brings sand in, and the sand covers up the peat. Okay. But the weight of all that sand on top of it is starting to cause it to change, because now it's insulated from the sun. It's getting pressed deeper into earth. And remember, we talked about the temperature gets hotter the deeper into the earth you go. So it's getting warmer, and it's feeling a ton of pressure from all the sand on top of it. So it's starting to then turn into, on the bottom picture, the pressure turns that peat into actual coal. So down below the surface of the earth, if you dug down, there's actual just coal sitting down there. Okay. Layers of coal.
Why do they call it peat?
I don't know.
Coal mines, right?
Coal mines. Yeah. Sam says, well, okay, so I've heard of coal mines. Yeah. So even like the seven dwarfs, the hi ho, off to work we go. They were miners, right? They were down digging. But coal mining is something that we hear about that still happens today. And so there are miners. They dig these tunnels under the ground so that they can harvest and bring up all of the coal underneath the ground, because we can burn that coal and use it for energy and heat. Okay.
Like on the train.
Okay.
Isn't the world trying to like reduce the burning coal bad for the environment?
Okay. Zeke says he's heard that burning coal is bad for the environment. And we're looking for cleaner sources of energy. Yes. However, up until our recent history, we didn't know that burning coal was bad. So this is something that has been done for hundreds of years at this point, the mining of coal and using it for energy. They are breaking away from that, but it is a natural resource that we do have. Okay.
That we're meant to use.
Now, the other pictures on the right, it shows oil and gas. This one is showing in the ocean, but it also happens on land. Dead organisms fall to the ocean floor, and then they get buried in all of the sediment down on the ocean floor. Again, the ocean floor is constantly moving because the water is constantly moving. So it's moving the sand around on top of all of those dead organisms and covering them up pretty easily. And again, the pressure weighs it down, and it forms oils and gases down under the ocean. And in that bottom picture on the right, you see underneath where the oil and gases are, but on top of the land, you see those little like the oil rig thing that pulls the oil up from underneath the ground. Okay. Yeah, Sam.
I have a question.
Yeah.
So like, I thought of like, how do we ever find fossils if they were like under like Africa or somewhere? Because when since they all moved away, how did they do that? I never saw that.
How did who do what?
The continents break apart? Yeah. From a giant earthquake, I think.
How did the continents drift apart?
Yeah. How would they find fossils if it's like under the continent? If
the fossils aren't under the whole continent, they're just like in like
the surface.
This, not the okay. I mean, I'm gonna have to go kind of deep, but I don't have to go like crazy deep. Okay, because remember when we just did an introduction to the four spheres, we said that there's like there's like the surface layer, then there's a harder layer, but then there's a liquid layer. So it's still in what would be considered the more surfacey layer. But so it's not like down like under the continents. It's not down like that deep. But it is fairly deep. And do they always know where they're looking? Sometimes scientists are digging and digging and digging, and then they find nothing. And then other times they're like, oh, this is where a whole bunch of dinosaurs died. Who knows? They don't always know. But the paleontologists, people that study bones and fossil remains, they have different things that they look for that help them know where to dig and where to look.
Aren't there like...
I am not a paleontologist,
You're a teacher.
so I am not sure what kind of clues they're looking for to find out if this area is a good place to dig or not. But I do know that it's not like crazy deep. Like it's, I mean, 50, 100 feet deep. Yeah. But which is more than you can dig with a shovel in your backyard. It's deeper than you can dig in your backyard, but it's not too deep for scientists with special drilling machines to get to. Okay. All right.
This one.
Yes.
So one way I've learned to I've seen I watch a lot of documentaries about stuff like science and stuff. So it's they a lot of times cliffs. There's it's easier to dig in the side of them, find fossils, and so I was wondering, so how does there no land?
Okay, let me paraphrase what Zeke said so far if you didn't hear. He said that he saw on like one of his nature National Geographic shows that he's watching that it's easier for them to find and dig into the side of a cliff. And that totally makes sense because that's like exposed rock. So you can literally see the layers of that exposed rock and they can be like, oh, here's some stuff right about here.
And then they find. Well, one thing is, how do they find how are the bones sometimes? Is this realistic or just on shows? Because sometimes I feel like the bones are all in the right the shape of the body.
He said he feels like a lot of times when he sees this that the fossils are just laying there in the shape of a body. And yes, that would make sense because if an animal dies, unless it got just completely torn apart, unless a T-Rex came and just tore it apart and threw pieces everywhere, like when something dies, I'm assuming it just kind of is just like, boop, right? And it just lays down where it's at. So its body is still going to be in the shape of its body. Like, I mean, you could draw a little chalk outline around the baby velociraptor or whatever. And I'm naming all dinosaurs. It doesn't have to be dinosaurs. Fossils aren't always just dinosaurs.
Old-time horses or something.
But yeah, so that helps the scientists, especially like early paleontologists, to figure out which bones connected together and why, because they could see the outline, like overall, of how the bones were near which bones were near each other.
Yeah, but it moves around in this rock.
Okay, he says, but I thought it moved around in the rock. It doesn't move that much. It's not like going way over here. Yes, it moves around, but not. I wouldn't think that much.
Or they can still see the body out.
And so you can see the layers in the canyon.
Yeah, like in a canyon or a cliff or something like that, you can see the layers of rock. Even if you're driving up to St. Louis, going up the interstate, and you see the rocks, you can, if you look closely, you can see layers in those rocks on the side of the interstate.
That's what I try to do with my
Yeah. Okay. So
I need to read it. We'll never get done. There's this place. We watched a video about it. I think in 4th grade, and it has a whole bunch of dinosaur fossils.
All right, yes, there are lots of places. I'm going to keep reading.
Wait, no, I have a really cool thing.
I have a really
I have something really cool that I remember.
Last thing, and then I am reading, Zekel.
Okay, so my grandma and grandpa's farm, we found evidence that it was actually water once because we found 3 fossils of we found 2 of an octopuses and one of a
Zeke found
jellyfish.
octopus fossils in his yard. He just
No, my grandma and grandpa's farm
in his grandma and grandpa's farm.
And a jellyfish. So we think that at some point in time that it was an ocean.
A jellyfish?
Okay, it was underwater. Okay, so Zeke can conclude at one point his grandparents' farm was underwater because in the ground they found octopus and jellyfish fossils.
Jellyfish don't have.
Yeah, but
Yeah, I'm curious about this because I wasn't sure what kind of bone structure they have.
I don't know about the jelly. It might have been 3 octopuses.
Yeah, I don't think that jellyfishes leaving too many bones around.
How big of a?
It's kind of a jelly, like not actual jelly. That would be Jason that would tell us about the jellyfish because he wrote a report about jellyfish in 3rd grade. All right, carrying on. Sometimes partly decayed parts of ocean organisms were buried deep under the ocean. There, a combination of heat, the weight of rock, and the action of bacteria turn the decayed materials into oil and natural gas. Oil and natural gas are also fossil fuels. Over time, natural gas and oil build up below Earth's surface, and the natural gas is often found above the oil. Today, in many parts of the world, oil and natural gas are pumped from deep below the ocean floor. Oil and natural gas are also found beneath land that used to be covered by oceans. Okay, turning the page. How old are fossils and fossil fuels? All right. Sean said, but how do you know the biosphere began 3.8 billion years ago? Yeah, you did ask me that a couple days ago. And I said, well, scientists have ways.
Look how much coal's there.
So here we go. Fossils can provide information about whether an organism is older or younger than other organisms. In general, each layer of rock is older than the layer above it and younger than the layer below it. This is called the law of superposition. So we don't have to remember law of superposition, but if you look at that picture to the right, basically what it's saying is the deeper you go, the older the rock. The rock on top is newer, younger rock, and the ones way down. So the flint is really old, and the limestone is fairly new.
Isn't it rated all the way?
Who said something?
I raised my hand, but then I answered my question.
Oh, okay. All right. If you found one fossil in a top layer of rock and another fossil in a lower layer, the relative age of the fossil in the lower layer is older than the fossil in the higher layer. This relative age of the rock is how old it is compared to another rock. So we talked about relative location yesterday, and now we've got relative age. So you know the age of one of them based on the age of the other. So if I found a fossil in the lava layer, looking at this picture, and I found a fossil in the sandstone layer, the sandstone is older or younger than the lava? Older. That is the relative age. Related to the lava, sandstone is old. But if I said sandstone related to flint, sandstone would be younger. Okay, so it just depends on which one you're comparing. So again, we have an example of that word relative, and it has to be, means that you're comparing it to something else. Okay, although you know that the bottom fossil is older, how can you tell whether it's 50,000 years old, 500,000 years old, or 5 million years old? The absolute age, oh, here we go. This was a word we just used yesterday. Okay, so if relative means we're comparing it to something, what is the absolute age going to mean?
Absolutely. It's like absolutely.
Yeah.
Thanks for Fiona raising your hand. Before it. I'm pretending I didn't hear people that didn't raise their hand.
Absolute age is just like absolute location. It tells you exactly what age they were when they died.
Okay. Right. Just like absolute location, absolute age is telling you the exact age. Okay. Absolute age is the age of a fossil in years. Write these down. Relative age, how old it is compared to another. And absolute age, actual age of a fossil in years. Write those two down. Okay. Isn't this fun how so many things are interconnected lately? It just makes me smile.
That's why I asked if we had to write it down.
Yeah. Pretty much if it's in yellow, it's a yellow highlighted word, we're probably going to write that.
And my older sister found 2 bones in our creek.
Oh.
All right. Hang on. Thank you for sharing. Hang on. All right. So, but how on earth could they figure out the absolute age of something all the way down in sandstone or flint?
The inside of the bones. The stuff you're talking about,
okay.
Like squishier, like the slime marrow.
Yeah. All right. To find the absolute age of a fossil, you have to find the absolute age of the rock in which the fossil was found. Since the fossil formed when the rock formed, the fossil is the same age as the rock. But how can you tell how old a rock is?
The layers.
All rocks contain different elements. Remember yesterday we talked about carbon being an element and oxygen being an element. Okay. Lily's eyes are like, yes, science. All right. Okay. All rocks contain different elements, and some of these elements change to other elements in predictable ways. What? Hang on. For example, element A, whatever that is, changes into element B over time.
So limestone and lava, basically.
Okay. If half of element A changes to element B every 1 million years, after 1 million years have passed, then the rock has equal amounts of A and B. So let's see if we can figure this out. I got element A and I got element B. Okay. A and B. We're good here. I need to change the camera so everybody can see me. All right. I got element A, blue scissors, element B, purple scissors. Okay. So after 1 million years, the blue is going to turn purple. So I know if I've got purple scissors, it's at least 1 million years old, right? Because it takes 1 million years for the purple scissors to be created. But if I've got a scissor that's half and half, then it means it's maybe been how many years? About 500,000 years, right? Because only half of it has had time to change. Does that make sense? So they're looking at all of the different elements that are inside these rocks and comparing them to how long it takes them to make whatever changes they make. And so it takes a long time and a lot of math for them to figure this out. But they can look at that and figure it out. Okay. The time it takes for the amount of an element to be cut in half is called the element's half-life. So the amount of time it takes for these scissors to turn from blue to blue and purple halfway is called the half-life. So, okay, I'm blue scissors, and it's a long time, and it's a long time, and it's a long time, and now I have reached my half-life.
I thought it should be the opposite.
Okay.
Purple turns into blue.
Half-life. It's halfway to its ultimate destination. Does that make sense?
Yeah.
Okay. All right. Yes. Okay. Scientists compare the amount of the elements in the rocks to figure out their age. They've used the relative ages and absolute ages of fossils to develop the history of Earth since its formation 4.6 billion years ago. One of the big, it doesn't say it in our book, but I will just tell you that one of the big things that they use, one of the main elements that they use to date the age of something is carbon. The process is actually called carbon dating.
I've heard that word.
You've heard that before. All right, I like that. But yeah, the process they use to age things is called carbon dating. And the main element that they like to look at is carbon, because every living thing has carbon. Okay. Josie.
How do they know, like, do they know the age of other planets? Because, like, Mars, if they know and have been on, like, have had things on there and they know how to do it on Earth, do they know how old the other planets are? Like, I'm wondering what the first planet was. Like, I've always wondered that.
That's a really good question, Josie, and I'm not sure if we know that answer yet. And I don't know if the math facts that we use to figure out carbon dating and things like that on our planet would work on Mars. We know what elements we have discovered so far, 100 something of them, 130, 40, 50-ish. Okay. And other planets, especially the planets we haven't got to yet, might have different elements, and they might be affected differently. So we know how things age on our planet based on our atmosphere, the temperatures, those kinds of things are distance from the sun. But being a different distance from the sun may cause things to age at a different rate. So the process we use to date things on Earth, I don't know if that process works on the other planets. But that's a good question that I can see if I can find.
Different.
Wonderwall, Wonder notebook pad.
What are we writing on?
I'm saying, does carbon dating work on other planets? Okay. All right. While we're going to move on, and I'll look up that in a minute. Okay. Okay. Scientists have used the relative age, blah, blah, blah. I said that. When describing the age of Earth, scientists use units called eras. Write this one down. An era is a unit of time measured in millions of years. A geologic period divides an era into a smaller unit of time. Sam.
I know about eras.
He knows about eras.
Yeah, there's like in baseball, there's the dead ball era, there's the steroid era.
Not the same thing.
Yeah, I know.
But, okay, he was comparing it. Baseball has apparently eras of time. And in scientific terms, era describes millions of years. Yeah. Baseball itself isn't millions of years old. So they're just talking about a large chunk of time in baseball. Okay, yeah. But actual scientific terms, an era actually lasts for millions of years. Okay. And if you look at the bottom of these two pages, it has geological eras that run all the way across in like a little colorful rainbow, starting with the Precambrian era over here, and then it goes to purple, the Paleozoic era. It says age of ancient life, and you see like this creepy little fishy guy and a fossil. Okay. And then on the next, you see the green, the Mesozoic era. It says age of dominant reptiles. What do you think that means? Age of dominant reptiles. And below it, it's divided into Triassic, Jurassic, and Cretaceous.
Ooh, that's dinosaurs.
Oh, who are the dominant reptiles?
The dinosaurs.
They're the dinosaurs. Okay, that's the era. The green one is where the dinosaurs were. And then we have the Cenozoic period, which is the age of dominant mammals.
Which is, wait, that's a stink.
Who are the dominant mammals?
That's a stink bug. Stink bugs are about to be a stink.
Okay, all right. Now, let's finish this page really quickly. Hang on. All right, Josie.
Will there be like another era? Because do you think that humans will evolve even more? Or will there be just more of that era, or will there be a completely new era, you think?
That's a fantastic question, Josie. What do you guys think? Will there eventually be another era and they'll look back at, oh, that was the time of the humans? Will things eventually evolve and there will be like a new version of humans or a better version or something else entirely? Era of
Bionic humans.
bionic humans. We're all turning into Iron Man. Cyborgs, okay. Sam.
Kind of like a zombie movie series.
Zombies, okay, era of the zombies.
No, like a zombie movie. Like each they keep evolving. Like first they're all bad,
And then they crawl.
then it gets easier, then it gets harder. Then
Wait, no.
super
Call of Duty.
No, I'm not talking video games here, guys. I'm talking real life. Could humans continue to evolve? Now, this is over the span of 1,000,000 years or more.
Oh, then yes.
Could we continue to evolve into something
Yes.
even better? And there'd be a whole new era. And then someday, millions of years from now, fifth graders are sitting here learning and they're like, oh, age of the humans. Ha ha ha. That was forever ago.
When we
Grace is like, oh, this is so silly. Okay.
Dinosaurs.
I like the way we are.
All right. I'm going to finish this chapter up, yo. Here we go. Fossil fuels formed hundreds of millions of years ago during the Carboniferous period. Find Carboniferous on your chart.
Found it. It's in the age of ancient life.
It's in the age of ancient life, Grayson says, down below that creepy fish fossil. Okay, in the purple. So fossil fuels formed hundreds of millions of years ago, that long ago, before us, even before the dinosaurs. And when they're talking about ancient life, they're literally talking about the very first, like what we would recognize as real organisms, not just the little bacterias and not just the little bitty teensy little things, like actual like creatures. Yes. Okay. Organisms. Okay. Why did there need to be actual creatures for fossil fuels to form?
Because fossil fuels are fossils.
Because fossil fuels are made of fossils. And if there were no organisms to die and decompose, would we have fossils?
No. We wouldn't have anything. We wouldn't even be here.
We weren't there. It was Carboniferous.
No,
It was just that scary fish guy. Okay. It was just that guy. Just that one guy. Scary fish guy. And the fossil fuels came from him. It wasn't just that one guy. I'm joking. Okay. All right. During this time, the land was covered. Nothing. During this time, the land was covered with swamps filled with large leafy plants. And over millions of years, these plants were buried and turned into fossil fuels. And as the tectonic plates moved, that's like the things that cause the earthquakes way down under. Okay. As the tectonic plates moved, the fossil fuels moved around. Okay. Because of this plate movement, coal is found in Northern Europe, Asia, and Midwestern and Eastern North America. Okay. And you guys ask, how did Pangea move? Lots of different theories. Lots of different theories. Don't know the right answer. Josie.
What was Pangea?
When all the continents
out of all of the layers of the Earth, which one is the tectonic plate in?
Good question that I don't know off the top of my head.
There's Jurassic in here.
Yeah.
But that's easy enough to find out. We will probably actually learn that when we get to geosphere.
Are we reading any more?
Tectonic
What do we have to
plates.
do before this?
Okay, so
We are talking about geosphere, right?
we are kind of talking about how geosphere and what? Biosphere are interacting. Yeah, so today we are talking about biosphere, but kind of like biosphere after the fact, and how the things are decomposing and turning into, the biosphere is becoming a part of the geosphere. Okay. So yesterday, how we talked about how the cycle just constantly goes. So today, it's kind of the end of the biosphere cycle. Biosphere turns into the geosphere. But again, all these fuels and nutrients are going to come back up. The fuels are going to come back up so that we have breathable air. The plants have breathable air. We have breathable air. And the nutrients are going to come back up so that the plants can grow. And the cycle starts over and over and over. So we kind of talked about the whole biosphere cycle, how it all flows. Okay. Tomorrow we're going to have not a quiz, not a test, but we are going to have a worksheet that kind of goes over all the biosphere stuff that we've talked about in our book this week. Will you be able to use your book?
No. The science book, no.
Undecided.
What about your
If you can use your book, then it's an open book assignment.
Definitely can use your notes. So I hope you've been a note taker, as I advised. Possibly your book, but I'm leaning towards notes. We'll see how it goes tomorrow. We'll see how friendly I'm feeling for Friday. Okay. All right, that's all I've got for science today. I know my friends still have some math and Hatchet to work on, so we're going to spend the next little bit working on that. So we will see you guys later for writing. Okay? Have a great rest of your morning.
Toodaloo.
Toodles. Oh, toodles.
I was just thinking that.